Hello guys. I am about to cry. I recorded like 50-minute, video of me going over the rest of this notes and I didn't save. Oh my goodness, So I'm gonna go ahead and I don't know, maybe it was too long. I'm gonna probably go ahead and go over the examples only here, like examples 3, 4, 5, and 6, because I know you want to get started on your work. You want to see these examples first, and then I may start and another one that just goes over some of these tables and notes. So sorry if there's a delay in uploading my notes. But what I'm gonna do with you is I'm gonna go over the examples 3, 4, 5, and 6 in this video. And then I think after watching those, you should be able to do the homeworks, okay? But I did post, what's it called? I did post this filled out copy of this. This is going to take forever to erase everything. So if you go to Canvas, some of you will probably notice this first, that the note that I just went on talking all by myself, but it's beautiful. I mean, I posted that up here for you if you want to see my first attempt, but here I go. I'm going to try to record one more time, and hopefully this time it stays. I'm going to go ahead and open this on my note. And then instead of me erasing everything that I did, let me see. And I'll go over examples 3, 4, and 5 here, okay? 3, 4, 5, and 6 in this, okay? All right, so go to page, what page are we? Page 5 for me. We're using something called the derivative test for relative extrema. They look somewhat confusing, but let's read it together. We have a relative minimum. If to that point C, we're going to say that C is a potential critical value, but we're going to say that point C is a relative minimum if it's decreasing to the left of it and is increasing to the right of it. And it makes so much sense in a picture. So let me draw a picture for you. If it's let me say this is your C. If it's decreasing, going down from left to right to C, but if it's going up to the right of C, then we call this relative minimum. Okay? The second case, number 2, we call this relative maximum. This point C is a relative maximum if it's increasing to the left and then decreasing to the right of C. So something like if this is your C right here, it's going up, increasing to the left of it, and it's decreasing to the right of it. If you have a picture like that, then we call this relative maximum. So they have to change. To the left and to the right, they should be doing something different. Now, we may have a critical point, a critical value C, but they can be neither a relative maximum or relative minimum if the derivative has the same sign to the left and right of it. And we'll see those cases, and I know I did it. I think the last one, example 6, we will see that case where it is a critical value, but it's not a relative maximum or minimum because the sign of the derivative doesn't change to the left and right of it, okay? But let's go ahead and do the short examples first, example 3 and 4. And who knows, maybe I will stop this video to see if it actually saved on my iPad this time. Alrighty, example 3, consider the function f given by f of x equals x squared minus 4x plus 2. They want you to find any critical values. And in order for you to find any critical values, you want to find the x values that will make the derivative 0 or where the function doesn't have a derivative. So start by finding f prime of x. Okay? Start by finding f prime of x. All right. F prime of x is equal to, I'll take the derivative of this for me, 2x minus 4, right? Now let's think about this. This is a linear function, 2x minus 4. This is defined everywhere. So we're not going to have a point where the derivative doesn't exist. So what we're going to do is we're going to set this equal to 0 because critical value, the first case, this happens when the derivative is equal to 0. Add 4 to both sides. Divide by 2. We get the first critical value to be, well, the only critical value to be at x equals 2. So what you're going to do is you're going to plot 2 right in the middle. 2 right in the middle. And you're going to test the sign of the derivative to the left of it and to the right of it. Okay? So use the derivative function which you found together, which is this 2x minus 4. You're going to use that. Give me a number that's to the left of 2. What's the number that is smaller than 2? And that will be like 1, right? All right. So if you plug in 1 into your f prime, you're going to get 2 times 1 minus 4. That's 2 minus 4. And not that we care about the numerical value, but this just came out to be what? Negative, right? When the derivative comes out to be a negative value, we know our function is decreasing in that interval. So write down that this is decreasing. All right, let's check the right side of this graph. So pick a number that's greater than 2. I'm going to test f prime of 3. Okay, if I plug in 3 into the derivative, 2 times 3 minus 4 will give me 6 minus 4, a positive number. So if the derivative came out to be positive, what do you know? This interval, we are increasing. This function f of x is increasing there. So notice the behavior change, decreasing to increasing. So this critical value right here is a relative extrema, okay? And now which one is it going to be? Now I'm going to sketch it real quick, okay? On top of this, if I sketch it real quick, it's decreasing from left to this point. It's going down. But at that point, it's going to go back up, increase, right? So what would you call this point? This point right here is the lowest point of this curve. So we will call this relative minimum, okay? Alrighty, so let's fill out these 3 blanks over here. F is increasing over the interval 2 to positive infinity. And is E decreasing over the interval to the left of that positive 2. And we just found a relative minimum. Change that typo to relative minimum for me. We do not have a relative maximum. And that point is going to be at 2 comma. What is the y value? Well, this is a little tedious part of this section. You're going to have to plug in your critical value into the original function, to find the corresponding y value. So 2 squared minus 4 times 2. This is where you do not plug into the derivative, so be careful, okay? 4 minus 8 plus 2, that will be negative 4 plus 2. We get the y value to be negative 2. So that's it. That's how you find the critical values, and that's how you find the relative minimum or maximum by plugging into the derivative and getting the signs. All right, let's try one more, example number 4. Consider the function g is given by g of x equals 2x cubed plus 5x minus 2. It's really similar to the one that we just did, but I wanted to put this one up here because this is a little different case. Find any critical values. So you want to find g prime of x first. That's going to be, take the derivative of this for me. What's that going to be? 6x squared plus 5, right? Now, this is a quadratic function, and domain of a quadratic function is always all real. So I know we're not going to have any places where we're not going to have the derivative defined. So what we're going to do is we're just going to set it equal to 0 and find the x values that will make this equation true. Subtract 5 from both sides. You get negative 5 equals 6x squared. Divide both sides by 6. Oh, look at that. What we're going to get is x squared equals negative 5 over 6. Can you square a number and get a negative number? No, right? Not in the real world or real number system. So say that you didn't notice that and you're just trying to take square root of it. And hopefully by then you notice, oh, this one has no solution. No real solution, right? So guess what? A, when they ask you to, hey, find any critical values, what are you going to tell them? Hey, there is no critical values. No real critical values. All right, if we don't have any critical values, then we're not going to say that we have any relative extrema. So B, find any relative extrema. Say no relative extrema. I saw this on your homework, so I said, why not? Let me include an example just like that so that we go over it together. All right. I think I'm going to keep on going. I think my iPad should be able to handle 2 more examples. The other 2 are a little bit longer, but all right, we can do this. All right, number 5. Consider the function f of x. Ooh, look at this one. This one's a little bit longer. It's a cubic polynomial, but same drill. Let's find any critical values. First, find f prime of x and set it equal to 0 for me. Okay, now all the examples that I'm giving you are polynomial functions today. So we're not going to have to worry about where the derivative doesn't exist. We may look at something like that in another day. But I think for polynomials, there'll be enough for us for now. Okay, all right, let's find the derivative. F prime of x is equal to, now take a look, 4x cubed will turn into 12x squared minus 9x squared. That will give you minus 18x, and then minus 30x. If you take the derivative of that, you will get minus 30, and 25 will just give you 0. So we found the derivative. All right. Now, I don't have to look at the original function until I need to find the y values later. So I'm just going to go from here. Okay? Set this equal to 0, and let's see what we can factor out. We have 12, 18, and 30. Looks like we can factor out 6. If you factor out 6, you're going to get 2x squared minus 3x minus 5. Now you need to factor this polynomial, this trinomial. So let me do the work on the side. Factor, I am factoring 2x squared minus 3x minus 5 so that I can solve for 0. And you know how I factor. I use my slide and divide method. I'm going to slide that 2 to the constant and multiply to get 2 times 5, 10. I factor that trinomial. 5 times 2 is 10, and 5 is negative, 2 is positive. But don't forget, I need to now divide by that 2. Now, if it divides, like this one right here, I'm going to write it as x plus 1. 2 divided by 2 is just 1. But 5 cannot be divided by 2. So what do I have to do? I have to bring that in front. So I'll get 2x minus 5. That's how I factor. Up to you, however you want to factor. You may use guess and check, but just show me some kind of work on your classwork or on your exam so that I know how you are factoring this. Okay. So I got my derivatives all factored out. We're ready to set these equal to 0. When does 2x minus 5 equal 0? When x is equal to 5 over 2, right? When does this equal 0? Well, that's going to be when x equals negative 1. So guess what? We have 2 critical values. We're going to have to create a number line with these 2 critical values. So the left one is negative 1 and the right one is 5 over 2. Now, let me write down f prime of x above here so that we can see where we are plugging these into. We have to do 6 times 2x minus 5 times x plus 1. So let's start plugging in some values, okay? So let's see, to the left of it. To the left of negative 1, give me a number that we can plug in. Let's plug in negative 2. A number that's smaller than negative 1. We'll go into f prime now. That will give us 6 times 2 times negative 2 minus 5 and negative 2 plus 1. I'm just plugging this into our derivative function. And what we are trying to do is we're trying to get the sign of the derivative. All right, what's that going to be? 6 times negative 4 minus 5 times negative 1. That will be 6 times negative 9 times negative 1. So look, this is a positive times a negative times a negative. If you multiply these signs, you will get a positive answer, right? If that derivative came out to be positive, what we know is that this section is increasing. F of x is increasing from negative infinity to negative 1. Alrighty, let's find the interval in the middle. Interval in the middle is from a negative 1 to positive 5 over 2. So what will be a what will be a good value to plug in? I'm gonna plug in 0, right? Because 0 is in between negative number and a positive number. So if I plug in 0, I'm gonna get 6 times 2 times 0 minus 5 and 0 plus 1. What's that gonna be? That's gonna be 6 times negative 5 times 1. Look, we're multiplying a positive times negative times a positive. What will be the sign here? The sign will be negative. Therefore, what we know is from negative 1 to 5 over 2, our function is decreasing. Notice that it changed, right? It was increasing to the left, decreasing to the right. So we're going to say that is a relative extrema, and we'll tell which one it is after sketching a quick graph, okay? Last interval. Let's do this one right here, all the way on the right side. Okay, what's a good number that we can plug in here? Do I have room? I'll just try to squeeze in the work here. Let's find f prime of, let's see, 3. I'm going to plug in 3 here. 3 is bigger than 5 over 2, so I'm going to plug in 3 into the derivative. 6 times 2 times 3 minus 5 times 3 plus 1. That will give us 6 times 6 minus 5 is 1. And the last number will be 4. Well, look at that. We're multiplying a positive number, and a positive number. If you multiply them, of course, you're going to get a positive number back. So what we know is from interval 5 over 2 to infinity, this function f of x will be increasing. All right. So if I try to sketch a general picture, not like an exact perfect picture, what I'm going to have is something like this. Here's my negative 1, and here's my 5 over 2, like let's say, 5 over 2 right here. The graph will look something like that. I'm completely ignoring the other part of the graph. Of course, you can graph this using your graphing calculator, but increasing from this point to all the way to the negative to negative 1, and then at that point, it's going to decrease. It's going to go down, and at that point, it's going to go back up. Of course, it's not accurate because I didn't plot the x-intercept or y-intercepts or anything. But then the reason I did this is because I want to call that this point is going to be your relative what? Maximum. And this point right there is going to be a relative minimum. Okay. Now, guys, we have enough to fill out all these blanks here. Okay. So, f of x is increasing over the interval negative infinity to negative 1. And 5 over 2 to positive infinity. And it's decreasing over the interval negative 1 to 5 over 2. We have a relative maximum at negative 1, comma. Well, here's the thing. We have to plug in negative 1 back into the original function, okay? F of negative 1 equals, now, you know, guys, I did this one earlier when I was recording all by myself. When no one was watching because the video got lost. I'm just going to go ahead and look at my notes. Because, you know, it's just you plugging negative 1 back into the original function. And you can try that. What was the value that I got? It came out to be 42. That comes out to be 42. So the y value is 42. And the relative minimum point, remember, it was 5 over 2 for the x value. So what you're going to have to do is find f of 5 over 2. And it took me some time too, because but that came out to be negative 175 over 4. Okay, so that's going to be your y value. And how did I get these y value? Just plug into the original function, okay? But that's it. That's how you will do number 5. And notice how I took the entire page because I was showing work, right? Alrighty, one more example, and then you're ready to try 2 on your own. Okay, this one is going to be a little special, though. Now, notice the previous one that we just did. It was going like increasing, decreasing, and then increasing, decreasing, and increasing. It was switching, but that's not always going to happen. And so if it doesn't happen, then we can't really call those critical values relative maximum or relative minimum. We're going to see that on example number 6. Okay, all right, it says find relative extrema and sketch the graph of the function. All right, change that to function for me. F, and F is given by this right here. So, well, you know the drill. Let's find the critical values first. Critical values. Find f prime of x, which is going to be 6x squared minus 4x cubed, and we're going to set it equal to 0. All right, let's factor what they have in common. The greatest common factor looks like 2x squared. If I factor out 2x squared, I'm going to get 3 minus 2x. Once it is completely factored, I'm going to set each of these factors equal to 0. 2x squared equals 0. If I solve this, I get 2x equals 0. I'm sorry, x squared equals 0. So the first critical value is at x equals 0. Let me solve this one. When does 3 minus 2x equal 0? Well, that's true when we get negative 2x equals negative 3. And x is positive 3 over 2. All right, we got critical values. We got 2 of them. So what we're going to do now is we're going to create a number line. I'm going to create a number line. Put the small number 0 on the left. Put the big number 3 over 2 on the right. Now we got 1, 2, 3 intervals to test, right? Now your f prime of x. We get so many emails nowadays. F prime of x is 2x squared times 3 minus 2x. I am going to use this function, this derivative, to find the signs, okay? So you ready? Let's plug in something to the left of it, to the left of 0. Any number that's negative will work. Let's find f prime of negative 1. 2 times negative 1 squared times 3 minus 2 times negative 1. That will give me 2 times positive 1 times, what's that going to be? 3 plus 2, huh? So the signs are going to be positive number times another positive number. If I multiply 3 positive numbers together, I know the derivative will turn out to be a positive number. So what we know is that to the left of 0, this function is increasing. All right, let's test the middle interval. Now, I don't know if you remember this thingy about multiplicity and the behavior at the x-axis that we talked about in pre-calculus class. Notice how x squared has even multiplicity, so it's going to bounce or touch the x-axis and go right back up. I'm expecting to get an increasing or positive derivative here again. Well, let's see. All right, what's the number that's in between 0 and 3 over 2? Let's find f prime of 1. 1's bigger than 0, but 1 is smaller than 3 over 2, so 1's perfect. 2 times 1 squared times 3 minus 2 times 1. That's going to be 2 times 1 times 3 minus 2. Well, the signs are going to be positive times another positive. Look, if you multiply 3 positive numbers together, you will get a positive product. So again, this section came out to be a positive derivative. Therefore, we know f of x will be increasing in that interval. Ooh, look at that. Well, 0 is a critical value, but it's not going to be a relative maximum or minimum because the behavior to the left and right is still the same. The sign of the derivative to the left of 0 and the right is the same. All right, let's check the last interval. Last one, I just need something greater than 3 over 2. Something greater than 3 over 2. So let me plug in, 4 this time. All right, if I plug in 4, just a random big number that I could think of, then I'm going to get 2 times 4 squared times 3 minus 2 times 4. Let's see what that is. That is 2 times positive 16 times 3 minus 8. That's going to be a positive number times a positive number times 3 minus 8 is going to be negative number. So if I multiply positive times a positive times negative, I'm going to get a negative product. So negative derivative means my function is decreasing on this interval 3/2 to positive infinity. And I really didn't write the intervals here, but I know you have no issue writing the intervals. This one was 0 to positive 3/2, and the one all the way on the left was negative infinity to 0. All right, now let me sketch a quick graph, okay? I'm not gonna make this graph a perfect graph, but you know, just a sketch. Here's my 0, here's my 3/2. What I'm gonna have is a graph that is increasing, and it's still increasing, but it's gonna start decreasing there. I think I should fix this part. Increasing, kind of increasing and decreasing. So what we know is that this point right here is gonna be our relative maximum. But this point right here is not going to be it's neither relative minimum or maximum, because it's still increasing to the left and to the right of it. So let's go ahead and fill out the blanks that we have. F is increasing over the interval. We found two of them, right? Negative infinity to 0 and 0 to 3/2. F is decreasing over the interval 3/2 to positive infinity. Now, we did have a relative maximum at 3/2, right? At 3/2. So what you're going to do is we have a relative maximum at 3/2, comma. Now, listen, we need to find the y value. So what you will need to do is find f of 3/2. And f of 3/2, I found it when I was recording all by myself, remember? So let me just use that number that I got earlier. If I plug in 3/2, I got 27/16. So the y value will be 27/16. But listen, this is one point where we actually use the original function. And that's when you're looking for the y value, you got to plug it into the original function, okay, not the derivative function. All right, last part is saying f has a critical value at x equals 0, right? We did have a critical value at x equals 0, but then the critical point is 0. Now, if you plug in 0 in here and there, what will you get for the y value? You will just get 0, right? So the order pair will be 0, 0. And that one was neither a minimum or maximum value, because the sign to the left of it was positive, and the sign to the right of it was positive. So if it continued to increase and increase, it didn't change. So because it didn't change, we're going to say this is neither a maximum or minimum, okay? I think one of the problems that you're going to do for me on your classwork is like that. So I'm going to come back and finish the middle section, okay? But if you were watching, you are ready to dive into these two problems for me. I'll wait for you to submit these, please, before March 29th, okay? I don't want to grade 30 papers on Sunday evening or Monday morning. So if you want to just submit them early, because I'm going to have new ones for you on Thursday to submit, that will be great, okay? Alrighty, come back, and if you want to watch the middle section, I'm going to have these in another one for you, okay? All right.